Okay, so in this section we're going to begin with mathematical propositions as we segue into logic. A proposition is a statement that is true or false, but not both. There are three examples listed right here. For example, the only even prime number is 2. This is actually a true statement. Okay, we are not interested necessarily in the validity of that yet. We may get to something like that in the next section, but for now we're just introducing terms and definitions and defining a proposition to simply be a statement that is true or false, but not both. Now, let's take a look at this definition, and let's say that I have two propositions, P, Q. So P is one proposition, Q is one proposition. And because they are propositions, they are statements that are either true or false, but not both. And so we would say the conjunction of P and Q, and this symbol right here is read and, is the proposition P and Q. Now we have a truth table. Remember, because P and Q are propositions, okay, each of them could be true or they could be false. And so we need to take a look at the four possible outcomes for each of these. And this is why it's 4. Okay, so the statement P could be true, it could be false. So there are two ways that statement P could be. Statement Q could be true or false. So there are two different ways that statement Q could be. If I multiply those together, I get 4. The idea is for all of these, as we're going to progress through and look at lots of these truth tables, P could be true, Q could be true, P could be true, Q could be false, P could be false and Q could be true, or lastly, both could be false. And so that's why there are 4 different cases that I have to specifically take a look at. Now, let's take a look at the truth table for the conjunction P and Q. If P is true, Q is true, then P and Q is true. But if either of the statements, P or Q, is false, then the conjunction P and Q is false. So this is important to notice that P and Q is true only when P and Q are true and false otherwise. Now, just like we had a conjunction, we have another one which is called a disjunction. So let's say that I have two propositions, P, Q. The disjunction of P and Q, notated P, and this is read P or Q, is the proposition P or Q. So we have a truth table for this disjunction as well. So remember, P could be true or P could be false. Q could be true or Q could be false. And so I have these 4 separate cases that could happen in tandem between my two statements. So if P is true, Q is true, then P or Q is true. If P is true, Q is false, then P or Q is true. If P is false, Q is true, then P or Q is true. And lastly, if P is false, Q is false, then P or Q is false. So what this is saying is that the OR connector, P or Q is true when P or Q is true, and false only when P and Q are false. So as long as one of P or Q is true, then the disjunction is true. But if both P and Q are false, then P or Q is also false. Now, let's take a look at an example down here. Use the disjunction truth table to assess if the disjunction is true or false. So, I'm going to make a very small table, P, Q, and the disjunction P, and this is read P or Q. So, here's my first statement. 2 is the only even prime number. Well, this statement is true. 2 is the only even prime number. Statement Q is 3 is a perfect square. What are perfect squares? That's what I get when I square a whole number. So, for example, 1, 4, 9, 16, 25, etc. So clearly, I can see that 3 is not a perfect square. So when I say 3 is a perfect square, that is a false statement. So when I look at the truth table, if P is true, Q is false, P or Q is true. So I would simply say that P or Q is true. Okay? Why is that? Well, one of them is true, namely P. Therefore, the disjunction P or Q is true. Now, this leads us to another definition, something called the negation. The negation of P, notated with this symbol right here, is the proposition not P. And often we read this simply as not. So the truth table for the negation of P is given as follows. So notice this time I don't have P, I don't have Q in tandem. I simply have one statement P, and I'm looking at the negation. So since I only have one statement P, P is either true or it's false. Well, if P is true, not P is false. And if P is false, then not P is true. So let's take a look at this example right here and see if we can't put some of all of these connectors together. So I have two statements. Okay? John, for statement P, John is enrolled in a mathematics course. And statement Q, John is enrolled in a computer science course. Now, what I simply want to do is I want to formulate or write each of these in English. So this first one, not P. So I simply wish to negate statement P. And so this would simply read, John is not in a math course. The negation of Q, John is not enrolled in a, I'm just going to abbreviate, computer science course. Okay. P and Q. Well, this is a possibility. John is in a math course and John is in a computer science course. What about P or Q? P or Q would simply be the statement, John is in a math or John is in a computer science course. One or the other. Okay, what about this next one? So P or not Q. So how would I formulate this? I would say John is in a math course or John is not in a computer science course. P and not Q. So in this one, I would say John is in a math course and John is not in a computer science course. Now this last one right here, not P and not Q. So how would we phrase this? We would simply say John is not enrolled in a math course and John is not enrolled in a computer science course. Now, let us construct a truth table for the proposition as follows. So let's say that I have this proposition right here, P, not P. So P could be true, P could be false. Okay? Now, not P, well, if P is true, then not P is false. And if P is false, then not P is true. Now, remember, this upside down connector right here, okay, is read or. So I would encourage you to possibly scroll back and look at this truth table right here as you work through it, perhaps. So P or not P. This is what this is stating right here. P or not P. Okay, well, if we remember with the logical connector or, okay, for the or to be true, I only need P or Q, or in this case, not P, to be true. So if P is true, not P is false, then P or not P is true. If P is false, not P is true, then P or not P is also true, because I had at least one truth statement. So notice that P or not P is always true. And we say that a compound proposition that is always true is called a tautology. This is a very important logical definition right here. A tautology is a compound proposition that is always true regardless of my statements, in this instance, P and not P. For example, okay, of two tautologies. If I were to say, today it will rain, or today it will not rain, this is really simply saying P or not P. Well, this compound proposition is true in all situations. It doesn't matter if it rains or if it does not rain, because today it will rain or today it will not rain. So we would simply say that this compound proposition is a tautology. Possibly my favorite tautology is the statement, we do not know what we do not know. This statement is true in all situations. Okay? So we would call it a tautology. Let's take a look at another example. Okay. So construct a truth table for the following propositions. So this is read P and Q and not P. P and Q and not P. So if I begin to fill in this truth table, so true, 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 false, false, true, or false, false. Okay? So those are the four cases that I could be in, depending upon if P or Q is true or false. So if I take a look at the connector and, okay, the connector and right here, remember the connector and is only true when both P and Q are true, and it is false everywhere else. Now, the negation of P. This simply says, look at the statement T or F in the P column and negate each of them. So if I negate them, this would then be false, false, true, true. So in this third column, I have this statement, okay, P and Q. And in the fourth column, I have this statement, not P. Now, I wish to assess P and Q and not P. So if we remember the and connector, okay, the and connector is only true when both P and Q, in this instance not P, okay, are both true. So a true and then a false is a false. A false and a false is a false. A false and a true is a false. And a false and a true is a false. The point is I only will get a true statement out of the and connector, okay, if my two statements are both true. Well, take a look at these two columns right here. Okay? In neither case are both P and Q and not P both true. Therefore, my final proposition right here is full of falses. So notice that P and Q and not P is always false. We say that a compound proposition that is always false is called a contradiction, and we will explore contradictions in the next unit. So, a couple of examples. If I were to say, it is raining and it is not raining, I'm contradicting myself. I'm saying two completely contradictory statements, okay? Second contradiction. All leprechauns are green, but some leprechauns are not green. So each of those are contradictory statements.